This video, we're going to be going through acid-base titrations. And so a titration is basically an experiment that uses a chemical reaction and a substance with a known concentration to find unknown concentration of the other reactant. So we're going to react two things together that we know the concentration of one of them, and then we can use the information about how much it took to neutralize or to fully react with to get the concentration of the other substance. So when we're doing strong acids and strong bases, it's basically going to be a double replacement reaction. Or we can call it an acid-base neutralization reaction. It's both. You see how we have the Na goes with the Cl to make NaCl, and then the H goes with the OH to make water. Think about water as HOH. Net ionic equation, though, is really helpful for us because really what's actually reacting and not just spectating is the hydroxide and the hydrogen make water. That's your net ionic. So if this is a 1-to-1 ratio, then we make one water here. So it, when we balance it, then we can look at different ratios there. Basically, when we do a full neutralization, the amount of hydroxide and the amount of hydrogen ion are the same. So the amount of acid stuff and base stuff is the same, and that is what makes the solution neutral. If we had a little bit extra H plus left over after neutralization, it wouldn't be fully neutralized, right? So the chemical reaction is, hey, we add enough to be fully neutralized. How much did it take of each thing? If this was 0.5 molar, then this would also be 0.5 molar, right? And so we can use known and unknown concentrations, or actually not molar, but amount. So this, like, if this is 0.5 moles, then this would be 0.5 moles when we get to that neutralization point. We call this point at neutralization the equivalence point. It's when the moles of hydroxide equal the moles of hydrogen ion. And we're specifically using hydrogen ion and not hydronium here. I mean, technically it's hydronium, right? But because I want you to focus on this net ionic equation that has just one water as the product, not H3O plus, right? So this would be a graph. If we graphed pH, and let's say we started with HCl, and we're going to titrate it with sodium hydroxide. So notice that we start at a low pH. This means it's acidic. So low pHs, remember, are acidic, and higher pHs are basic. And then, of course, in the middle, we have neutral. So we start acidic because we have HCl in our flask. Then we add a bunch of base. And we see here we have not a lot of change in pH. This is called the buffering region, which you can tell by the fact that the pH isn't changing very much. That's why we call it the buffer region. And then all of a sudden it shoots up. That's because we have gotten to the point where we're neutralizing our acid and all we have is base. And so our pH is going to shoot up. And right in the middle of this vertical area is what we call the equivalence point. So the equivalence point, remember, is when the moles of hydroxide equal the moles of hydrogen ion. So the moles of the acid and the moles of the base are the same. So the acid stuff and the base stuff are the same. And that equivalence point, however much we had to add to get to that point, this is the number that we would use in our math. We'd say, hey, it was about 25 milliliters of NaOH we needed to use, and we could then go figure out what the amount of acid there needed to be. And we could find the molarity of the acid. We already know the molarity here, but we could figure it out if we didn't know. If this were X, we could figure it out. So that's just a graph of what this titration is called, a titration curve. So here's a table kind of showing the same thing. So the volume of hydroxide added, the millimoles, or we can do moles is just, it's a bigger number, so or a smaller number, so we're using millimoles here. So the millimoles of H added, the amount of hydroxide added, the amount of OH remaining. So see how we start with only H plus, and then we go down to neutralize it. And the amount that we added is that point of neutralization. So the total volume of the solution. So our concentration of our hydrogen ion, once we get to neutralization, shows us that our pH is around 7. Right, so we start with a low pH and we get higher. And notice how it doesn't change very much, and then all of a sudden it shoots up. You'll see that when you do the actual lab, that it does that. If we keep going and adding hydroxide, notice that we don't have any more hydrogen ions, so all we have is just excess hydroxide. And see how our pH is very basic now. So we would be up here in these points. So this is a graph, or a table, data table, showing the same kind of thing as a titration curve, but also showing you how we're following the concentration of hydrogen ion and the pH, which is direct related, right? Or indirectly related. The lower the hydrogen ion concentration, the higher the pH. So this is a strong acid, strong base. When we're doing strong acid, strong base, the equivalence point, strong acid, strong base titrations is 7. Because we think about what we make in this chemical reaction. If you have a strong acid plus a strong base, you're going to make water plus a neutral salt. Remember when we talked about the salts being acidic, basic, or neutral? If you have a salt that comes from a strong acid and a strong base, it would be neutral for both the cation and the anion, so it'd be neutral salt. So that means that the pH of our neutralization point is 7. However, when we have a weak acid, strong base titration, let's think about what we have here. So weak acid plus strong base, we know makes the conjugate base and water. So if I were to put this with like sodium hydroxide, for example, so let me just write it out like this. And we're doing net ionic here, but let me just show you without the net ionic. Just showing you the other way we could write acetate. So this would not be neutral because this acetate ion is a conjugate base. So now we would have a basic salt at neutralization. At the equivalence point, our pH wouldn't be 7. It would be a little bit above. So pH at equivalence point, we would expect to be above 7 because this is a conjugate base, remember? It's not a neutral salt that we make. So that acetate ion is then going to react with water and it's going to make hydroxide again. And so this gives you that more basic, because we know that acetate ion is going to do base stuff. So essentially remembering that what our pHs look like at these different, for these different equivalence points. So we see here how the pH is higher than 7 at the equivalence point. Remember, the equivalence point is halfway down that very vertical line. And how much did we add to get that? Around 25. So we could use that number to help us do some math. So how could we find the pH at the equivalence point? Well, we would start with our initial concentration. We start with our original pH. So this is define the original pH. We just have our normal, this is without adding anything. we just have our initial pH, so that's initial, right? So the starting pH is just the initial amount of acetic acid we have, do our normal Ka stuff, find our pH. What if we titrate 10 milliliters? So let's just say, hey, we add 10 milliliters. We want to know what's the pH of 10 milliliters. So put our 10 milliliters of sodium hydroxide in there. That would be 1 mole with this molarity. We would do like a add change after type of situation. We would make 1 mole of the acetate, and we would have used up some of the acid. So then we would plug this in to Henderson-Hasselbalch and get our pH, because now we have a buffer. So that buffering region, we can use Henderson-Hasselbalch to help us with that. So you would use the after change table. You could kind of figure that out. So let's say we added our 25. We added a full 25. We have no acid remaining, only the base. And this is the millimoles here. But now we got to look at the total volume to get our new molarity to put into an ice table to figure out what our new pH is. So we can't use Henderson-Hasselbalch anymore because we don't have any of we don't have buffer anymore because you don't have acid. So when you don't have the acid anymore, you're not a buffer. So what we would do is we would say, okay, once we run out of the acid moles, then we have only the acetate ion. So we're going to say, let the acetate ion do its job. It's a base, right? So it'll do its job. Here's what we make. Do a whole ice table for this. Remember, we need the concentration, so we have to look at the new total volume. Yes, we started with 25. We titrated 25, but how much of this NaOH do we have? 25. So 25 plus 25 is 50. So new total volume. And then we'll do our thing, and we can find our OH concentration. Once we have OH, we can find our POH and subtract from 14. So here we have our equilibrium, our ice table. We have Ka of acetic acid, but we need Kb, so we'd use Ka times Kb equals Kw. Then we would get our OH, which is our X, get our POH, and subtract it from 14 to get your pH. So if you know you're not going to use, so like, this should be, I believe this is millimole, not mole. And this is millimole. So we started with 2.5. Initial 2.5 millimole. Because it's 25 times 0.1. Milliliters times molarity is millimole, and that can be helpful for you. So let me write that out for you. Milliliters times molarity equals millimole, and that can be helpful, quick way to look at this. Yeah, they didn't write this here. This is millimole, millimole. So if we know we have some remaining, we have the weak acid and its conjugate base, we're a buffer. Henderson-Hasselbalch. Okay. If you do this change table, right, and they're not doing the change table, I'll show you in class, we'll do the add change after. If you get to after and you have 0 of something, no Henderson-Hasselbalch. Take with the thing you have, we're going to have to figure out what the new concentration is, goes into the ice table, and then we just do it like we would do any other ice table. Find your Kb, because we're doing the base from our Ka, plug everything in, get your OH concentration. Can't take the negative log of that to get pH, but we can get POH, and we can subtract from 14 to get pH. So it's a lot of steps. So make sure that if you're confused on any part of the steps that you're asking for some support. Text me if you need some help moving forward. After the equivalence point, all the acetic acid is neutralized. So anything we add, it's just going to be OH. So all we need to do to find the pOH is just look at how much OH we have, divide it by the total volume, get my molarity, pOH, and pH. So we're going to have kind of different parts to what we're doing here. So if you're in the buffering region, so all this area, so we have initial, so this would be initial. You're going to use an ice table. Normal ice table. Then we have our buffering region. Use Henderson-Hasselbalch. Okay. Then you have your, well, that goes only to this point. So buffering, Henderson-Hasselbalch. And then you get to the point where you have no buffer, but you have conjugate base, ice table. And then at this point, once you're just adding a whole bunch of extra, so this bottom part, so this kind of four different phases. So 4, adding OH past neutralization. Just use OH concentration to get pH. And it's specifically excess, not total. Not total amount added, right? Because we remember we're adding, and then we get to that point where we're 0. How much more do we add over that? That's how we get this molarity. So this molarity is this millimoles divided by milliliters. Gets you molarity because the millis cancel. So there's 4 different kind of steps if you need to like figure out where you are, and then how do you find the pH? Initial table, initial pH, ice table. No buffer. No, you don't have buffer, only conjugate base left at your neutralization point. Ice table. Let me see. Let me just write maybe at neutralization. You need an ice table. So at neutralization. Now my pH might not be neutral here, but at neutralization, use an ice table. If you don't have that buffer, you can't use it. And then if we're going beyond that neutralization, you can just literally look at concentration of hydroxide to find pH. So it's a lot. So I want you to just try it out. See just how it goes. Go back to these notes. First start with your initial, and then see where you are. So when you add this much base, sodium hydroxide, right? Do we have some acetic acid left over? If we do, then you're still Henderson-Hasselbalch. If you get to the point where you don't have any left over, I'm assuming that they're going to do one of 3, right? So you have Henderson-Hasselbalch, neutralization, and then post-neutralization. But start with your initial pH. I'm going to add this in. Start with initial pH. And then essentially you could make your own graph with this. So I want you to try it. Just get as far as you can. Look back at the examples. So let's see. So our they didn't do the initial pH, but we can do that. So initial pH would be acetic acid with it before I add anything, plus water. Thanks, acetate. H3O plus. Oh, you need Ka. So if you haven't started it now because you need a Ka, then go ahead and pause and start it now. So my initial pH Hopefully by now you're pretty familiar with this, using x is small. Let's say x squared is equal to 1.8 times 10 to the negative 5 times 0.12. 2.16 times 10 to the negative 6. Take the square root. Okay. And then find error. So x is equal to hydronium. So my pH is a negative log of that number, which is 2.83. That's my initial pH. All right, now I'll do A, B, and C. This is just a warm up. So if I add let's go down here. So we got to get everything in moles. Millimoles is really helpful. So we can just do millimoles divided by milliliters, or millimoles. The molarity times milliliters is millimoles. So molarity is 0.12, which is the same thing as millimoles over milliliter. Just add the milli to both sides. Times milliliters is 6. So we start with 6 millimoles of our acetic acid. If we add 10 milliliters, that's 10 milliliters times the molarity of the base, which was 0.24. That's 2.4 millimoles of base, which means we do have enough acid to neutralize this base. And we have 0 of the, this is a little bit off, but this is the acetate here. Just color code this so it's a little bit off. So this is our addition, and then we have our change, which would be minus 2.4 minus 2.4 plus 2.4. And so we'll get our final answers, and then you see we have both the acid and the base, so we're going to do Henderson-Hasselbalch. Okay, so that'll get your pH. For the next part, 25 milliliters of the base, this is the equivalence point. Because the 25 milliliters of the base is, let's see. How do we know that's the equivalence point without doing math? They don't tell us. So if you do, let's get the millimoles here. So it's 25 milliliters of base times 0.24 molar equals 6 millimolars. So you know that this is going to be equivalence point because it's 6 millimoles of the so we'll have add, we have 6 millimoles. I need to probably do this in a separate page here. Okay, so we had our 6 millimoles. We also have 6 millimoles of our base. How did I get that? 0.24 molar times 25 milliliters. How did I get the previous 6 millimolar? 50 milliliters. 0.12 molar equals 6 millimolar. So we're going to subtract to neutralize, and we wind up with 0. And then we'll add. So we wind up at the end of the day with only the conjugate base. So we cannot do Henderson-Hasselbalch. So we got to do an ice table when you're at the equivalence point, which means you have totally neutralized both. You have no acid, so we don't have the Henderson-Hasselbalch. So we go to do our ice table. Where did I get this? Oh, that's the molarity. So now we need to get the molarity. So we'll take our 6 millimoles times what's our new concentration? So we added in 50 milliliters plus 25 milliliters equals 75 milliliters total. Not times. Divided by. That's going to give you the 0.08. And that's going to go into the initial. Then we do a normal ice table stuff. X is small. Got to use KB for this one since we're talking about the conjugate base. Remember, KW equals KA times KB. Then our X is equal to hydroxide, and we can get pH from there. So this should be, the only new stuff is like how to know which one to do, right? We've done Henderson-Hasselbalch, done ice tables. You got to figure out which one you're doing at which point. And then the last one, they didn't actually finish C in the textbook, huh? 35 milliliters of base. So if we do 35 milliliters of base, it's 0.240 molar of the base. So that's going to be 35 times 0.24. That's 8.400 millimoles. So we used up 6. So we have 2.40 millimoles left over. Why do I know I used up 6? Because that's how much it took to neutralize anything over that, right? How many milliliters was that? So that was 25 milliliters that went with the 6. So how many over was this? 35 minus 25 is 10 milliliters over. So we'll take our 2.4 millimoles divided by our 10 milliliters. And we'll get 0.24 molar hydroxide. And then we'll take the negative log of that. Zero 0.62. And then we'll get our pH. So we way overshot, right? So basically we're just trying to figure out how much over that equivalence point area did we get. The equivalence point area was 25 and 6. So we need to know, like, if we put in 35, how much over that 25 is it? It's 10 milliliters over and it's 2.4 millimolars over. So it's 0.2 molarity over that we have in excess. And then we would go from there. We're going to be doing this in class, so don't worry too much. Just maybe try to go back and see if you can work it. You can also do strong acid, weak base. You can imagine that when we do a strong acid, weak base, so we would have like NH3, for example, plus HCl. We're going to make NH4Cl, NH4Cl, which is a acidic salt. So our equivalence point, pH at equivalence, would be lower than 7. Because this is an acidic salt that we make when we put those two together. This one's not quite, it is a kind of a double replacement in that, I mean, I guess I can make it look like a double replacement. If we did NH4 plus and Cl minus, or you can kind of look at it like that if you want to. That one's a little bit weird because there's not a water in there. And there it technically is water, but it's not part of the reaction for this one. So you can actually just tell by looking at the graph what combination you have. If you see your equivalence point is below 7, you must have a strong acid, weak base. If you see your equivalence point is above 7, you must have a weak acid, a strong base. And if you have a pH at 7, you must have strong for both. Because we know that the resulting salt is either acidic, basic, or neutral. Okay. Why don't we try this one? Actually, let's leave this one for class. So if you want to try it, you can. I'm going to pull this out and we're going to look at it in class only. So if you want to try it for class, go ahead. But I'm going to do the explanation of it in class. An indicator is a thing that changes color at certain pHs. So you would want to get an indicator that changes color around your equivalence point. The endpoint is when you see that color change, and we don't want that endpoint to be really far away from the equivalence point. So if our endpoint is where the color changes and our equivalence point is similar, then that means we can use the color change as an indicator that we've gotten to the equivalence point. At the equivalence point, usually it does not going to change color yet, but like one tiny little drop over and it will change the color. So different indicators have different points in which they do change color. So you would pick based on what kind of equivalence point you think you're going to have. So if you think you're going to have an equivalence point closer to 7, we might use phenolphthalein because it's pretty close to 7. If you think you're going to have an equivalence point a little bit lower, you might use methyl red. A little bit above, you might use a different indicator. So here are just some colors, different colors of different indicators. So here's some common indicators and the ranges in which you would want to use them. Again, wherever you think your equivalence point is going to be, you want an indicator that is close to that. So what indicator would you use for the ones we've seen in these figures? So if you want to pull up this table, we can also look at it in class, pull up this table, you can figure out what indicators you would use for the graphs we've already seen, this one. So our equivalence point is around 5.5. So we want something that's going to change color. And we're adding, let's see, we're adding HCl for this one. So we're starting with a base and adding HCl. So we want something that changes color to acidic. So around 5.5. So maybe one of these guys would be good, or maybe this one. But see, this one starts to change color a little too early. So you want to make sure you get past that equivalence point. So maybe I would say this one because you don't want it to change too early. So we would use one that starts at blue and then turns to yellow. Well, actually, this would be too early because it's going to be going down. So we would actually want to use maybe this one. So think about it, like if I'm starting at high pH and going down, so I'm starting at say I'm starting at 12. I'm going to go down to 5.5. I want it to change color, not before I get to 5.5, but as close to 5.5 as I can. So I'm going to take anything that's above 5.5, which starts to change color at 6.2. I don't want that one. So I'm probably going to use this one actually. Or actually, this one is maybe better, 4.6. We'll just get as close as we can without going in that area that we don't want to be in. So think about a number line or like your graph, and you don't want it to change color before you get to that equivalence point. If you're starting from 12, you're going down to 5.5. We want it to be as close to 5.5, but not above it. So this one probably is the best option for that. Now, if we're doing starting at 1 and going up to 7, we would not want anything below 7. So this is a number below 7. So I maybe would start here, the cresol red. We use phenolphthalein a lot in class just because it's pretty easy because one side is colorless. It doesn't have like a color to color change, which is a little bit harder to see. So we usually use this when we're training new students. All right, that's all for this video. Well, I know it's a lot, but just keep doing practice with those ice tables and the Henderson-Hasselbalch equation and figuring out when you need to use them for those titrations.